Okay, so thank you very much for this very nice invitation. It's always for me a great pleasure to come here to Bergen. It's a joint work with Madi Jazim Hassan Al-Kaabi, a former PhD student of mine, which is now in Iraq, in Baghdad. Kurush Ebrahimi-Fard from NTNU, Hans Munthe-Kaas from here, from Bergen, and also Yuan Yuanchang, the Chinese PhD student who has now returned to China, and she got a position in central China in Henan University. Okay, so I'll start with a completely algebraic thing. By the way, I apologize for those of you who were in Reykjavik in Iceland, for those of you who were in Rosendal, and of course for those of you who were in both events, because this talk will be not completely different from what you have already heard. Sorry for that. There's tiny changes. So I start with a completely algebraic trick you can find in papers by Alexei Gavrilov from Novosibirsk. And it goes like this. You look at a vector space on some field, V, and you look at the tensor algebra, T of V. So it's the linear span of words with letters in a basis of V, if you want. And then you look at a bilinear product, triangle like this, from V cross V to V, but you don't suppose anything. It's not associative, it's not Lie, it's nothing. Just bilinear. Purely magmatic, we say in operatic language. And then I want to define a map, a linear map K from the tensor algebra into itself. And this is a recursive definition. So you send the empty word to the empty word and the letters to letters. But then you send a word. So it should be a K. It's a typo. You send the word to the first letter tensor by K of the tail here, and minus this sum. And you can see that big K of a word is the word itself plus corrective terms of smaller length. So the example with two letters, K of X tensor Y is X tensor Y minus the letter X triangle Y. Well, the linear combination of letters, I should say. And for three letters, you get a sum of 6 terms with alternate signs like this. And the inverse of K is even more manageable because you don't have alternate signs and you have a sum indexed on partitions of the set 1 up to n. And the term corresponding to the partition pi has length the number of blocks of your partitions. So it's like this, and the letters are made as follows. Call your block B, and spell it into B1, B2 up to BL in increasing order. You form this expression with triangles and parentheses all on the right, and then you order your blocks here according to their maximum. And this is the formula. So here you have an example with 2 letters and 3 letters. And here you recognize the 2 partitions of a set with 2 elements. And here you have 5 partitions for a set of 3 elements. Each of these partitions corresponds to one single term here. Okay, so now we come to differential geometry through affine connections. So for me, a connection will be just a covariant derivative operator on a vector bundle, and here specifically the tangent vector bundle. And the covariant derivative operators, as you probably know, it's linear with respect to the first variable, linear with respect to the C-infinity maps on your manifold, but you have a Leibniz rule if you multiply your second variable with a function, like this. Here it's an algebra talk, so I like to flip the triangle, and nabla xy is triangle y. Of course, the vector fields are equipped with a Lie bracket, which is called the Lie-Jacobi bracket, and defined like this. So a vector field is nothing but a derivation of the algebra of C-infinity maps, together with the locality condition. And the Lie bracket of two derivations is a derivation, so it's also a vector field, as you know. This is a Jacobi Lie bracket, and I denoted by this fat bracket. Okay, so now we have a vector space with some operation triangle plus a Lie bracket. So it's called the framed Lie algebra in Gavrilov's terminology. And you don't ask for any compatibility between the triangle and the bracket. Okay, so this is very well known. I recall what is the torsion and the curvature. The curvature makes sense in any vector bundle. The torsion is because the vector bundle is the tangent bundle itself. So you can define this. And of course, the interesting thing about torsion and curvature is that they are so-called tensorial quantities. That means that the torsion is C-infinity of M linear with respect to both arguments, and the curvature is C-infinity of M linear with respect to the three arguments. Okay. I just mentioned this. The torsion and the curvature are the building blocks of so-called special polynomials. So what do you do, basically? You compose, in some partial way, in an operatic sense, if you want, you compose the torsion and the curvature iteratively, and maybe the derivatives of the torsion and curvature. So I'll come to this in a moment. And if you compose all these things accordingly, you do generate a big family of quantities which are all tensorial. And there is a conjecture saying the contrary. That means any tensorial quantity is a special polynomial. We have only partial answer to this, but we don't get the conjecture yet. Okay, so now let me look at some particular examples. So the first example is the flat torsion-free case. For example, if your manifold is just R to the n, then the triangle verifies the pre-Lie identity. That means that it's not associative, but it verifies this weak form of associativity. The associator is symmetric with respect to the first two variables. So this notion dates back to Weinberg in 1963, and also to Gerstenhaber in the same year. But in Gerstenhaber's setting, you have also Kosul signs. You have a Z2 graded version of pre-Lie algebras. But you can trace back to a famous article by Cayley in 1857, and this article already relates vector fields on Rn and rooted trees. This correspondence is now perfectly understood in modern terms, in operatic terms, but it was already there quite a long time ago. Yeah, and the key of the story is the notion of free pre-Lie algebra, and Chapoton and Livernet 20 years ago, and also Jumadil-Dayev and Löfval proved that the free Lie algebra, the free pre-Lie algebra with one generator is given by rooted trees and grafting. So this is the formula for grafting. That means that you take tree number 1, you graft it on tree number 2 wherever you can, on the root, in the middle, or on the leaf here, and you sum up. Okay? And this is, the Preely relation is quite easy to show, and the freeness is a bit more involved, but it takes maybe 1 page. It's not a big deal. Okay. Now I go to the next case, which is the case when your connection is flat with constant torsion. So the flatness condition, okay, the curvature vanishes, and the constant torsion condition is written there. So let us look at what it means. You apply Leibniz rule. If you want to triangle x with this expression contains 3 terms, the t, the x, and the y. And then the 2 other terms, you switch them to the other side of the equal sign, and you see that this triangle onto 3 terms, it distributes over t, x, and y. And that's how you extend the connection from the tangent bundle to tensor powers of the tangent bundle or its dual. Okay, now the vector fields together with the triangle and the bracket, it's a so-called Postli algebra. So this notion is due to Bruno Vallette in 2007. But independently, Munthe-Kaas on the right has coined the notion of D-algebra, which is very close to this. And roughly speaking, it's not completely true, but roughly speaking, a D-algebra is the universal enveloping algebra of the Postli algebra. Okay. Okay, so what is a Postli algebra? So it's a frame D algebra, but with compatibility between the triangle and the bracket. The first axiom is easy to understand. It's a Leibniz rule. It's very natural. The second one looks a bit weird. So A bracket B triangle C is equal to this expression. But you can notice that the right-hand side is nothing but the Preely identity. Okay? But here, this right-hand side is not equal to 0, it is equal to this expression. So a Postli algebra with vanishing bracket is nothing but a Preely algebra. It's a way of summing up. Okay, so now what is the free Postli algebra? And you can find this in Bruno Vallette's paper and also in Munthe-Kaas on Wright's paper in the D-algebra version. So the free Postli algebra is the linear span of formal iterate Lie bracket of planar rooted trees with left grafting product. Okay. And here is an example. Okay, so there's two comments. There are 2 comments to be done here. First of all, you will say to me, okay, this one is just copy-pasted from the previous slide. That's true. But it has not the same meaning at all, because now the trees are planar. That means that here, for example, this middle tree, the long branch is on the left, and if the long branch were on the right, it would not be the same tree. And so this southeast arrow is not Preely anymore in the planar setting. It's just an avatar of the free magma. It's quite easy to show. And okay, so I give you the grafting product for trees, but now on the iterated Lie bracket, you get it just by forcing the Postli axioms. Okay, and if you want the D-algebra version of this, the free D-algebra is just the planar forest, and you also can graft by forcing the axioms of a D-algebra I don't recall here. Okay. So now, before I come to maybe a slightly more complicated stuff, there's a message to be taken. Now we are interested in manifolds with connection, with curvature, torsion, any connection. So the algebra of vector fields is not Postli algebra anymore, but the Postli formalism is still relevant. That's what I try to convince you of now. So it goes like this. There's a price to pay. You introduce an intermediate object, G tilde. It is the free Lie algebra over the vector field. And you have two versions, the free R Lie algebra and the free C infinity of M Lie algebra. Of course, the G is a quotient of G tilde. And this small g is the C infinity of M module of sections of a very big vector bundle, which is the vector bundle made of free Lie algebras over the tangent space at any point. Okay, so it's the same trick than before. You force the Postli axioms from V to these three objects, G tilde and G. So on G tilde, it's quite obvious, and you can mod out and go down to G. It's not very difficult to prove. So now we have two different Postli algebras associated with the situation. But now beware that we have two Lie brackets which are absolutely not equal. The fat one is internal to V, and the thin one is just a formal Lie bracket you have over a free Lie algebra. Okay, so there's a last trick. If you extend the scalars to the polynomials without constant terms, you make these objects positively graded. And extending the scalars to this, it basically means that you consider infinitesimal scalars. When I was in Mulhouse, I said to people it's a kind of a non-standard analysis of the algebraists. So, in more rigorous terms, it permits you to manipulate formal series without taking care of convergence. Okay, so two Lie brackets are not enough. I need a third one, which is called the Grossman-Larson bracket. And it works in any Postli algebra. If you have a Postli algebra, you can define this, and this is a three-line check to prove that the Jacobi identity is still verified. So you define the so-called Grossman-Larson bracket, but it is not C infinity bilinear, contrarily to the thin bracket. Okay, so now there's a funny thing about torsion and curvature. You can re-express them in terms of these brackets. And for example, the torsion is this sum of the three brackets, and the curvature is the difference of Grossman-Larson and Jacobi, triangle the third variable. So we re-expressed it like this, and this S of xy, we call them curvature elements. Okay, so now I come to a funny algebraic construction, which is called the Postli-Magnus expansion. So, now you look at G hat. What is G hat is the completion of G corresponding to the grading I told you before. And then, okay, so we have the Grossman-Larson bracket and the thin bracket. If you go to the enveloping algebra, suitably completed, you have a Grossman-Larson product, and so you have the associative product of the enveloping algebra. So you have two associative products. So you have two exponentials, one for each product. And it turns out that the image of G hat under both exponentials is exactly the same, this big G. It's described in terms of Hopf algebra structure. It's a space of group-like elements in the Hopf algebra. You have G hat, and you have two Hopf structures, one for the Grossman-Larson product, one for the dot product. But the coproduct is just the usual D-shuffle coproduct. It is the same for both structures. So the notion of group-like element is of course the same. Okay, so now you can go back and forth, this is the Postli-Magnus expansion. You go from G hat into itself by just doing this, and of course you can do the inverse. So chi and theta, and I displayed for you both at order 3. So it starts with X, it's a deformation of the identity, and starting from order 3, you can mix both the triangle and Riemann bracket, and the same for theta. And if the bracket vanishes, you end up with older Preli-Magnus expansion. You can also, and Preli-Magnus expansion, you can encounter it first in an old paper by Agrachev and Gamkrelidze. Okay. Okay, so I must spend a little time on these two diagrams. So these two diagrams are basically present already in Gavrilov's papers. And so, yeah, let's start with the leftmost diagram. So you have the tensor algebra on the vector fields, together with the Grossman-Larson product. Here you have the same, but with the dot product. I mean the tensor product of the tensor algebra. And it turns out that Gavrilov's K-map is an algebra morphism from there to there. On the left, you have the projection onto the tensor algebra, but now onto yeah. It's an isomorphism. Yeah, because again, I recall you that K is a deformation of the identity. K of a word is the word itself plus corrective terms of smaller length. So it's obviously a linear isomorphism. Okay, here you have the projection onto the tensor algebra, but with scalars, the C-infinity maps. Here it is the so-called higher order covariant derivative map. And what is the right hand side column? Here you have the universal enveloping algebra of V, this is the canonical projection. And this universal enveloping algebra projects onto the differential operators on your manifold. And this diagram commutes. And if you restrict to Lie elements, you get this diagram here. Okay. Okay, so another diagram I have to spend some time on. So I want to explain what is Gavrilov's double exponential. So this is my manifold M together with its connection. So when you have connections, you have geodesics. So you start from a first point. First point X here. Now on X, I give myself two directions, V of X and W of X. And I multiply them by two formal indeterminates T and S. Okay? Now, I want to follow the direction of given by V, by TV, I should say, along the geodesic during some unit of time. And I end up in the second point, which is y. Okay. Now, from y, I follow that direction, S big W. And what is big W? It's given from small w by parallel transporting this vector along this geodesic. Okay. And now I can continue the game. I follow this geodesic in the direction of big W, and I end up in a third point, which is Z. And now I want to go directly from X to Z, following this direction, which is the double exponential by definition of the two directions there. So it's a kind of geometric Baker-Campbell-Hausdorff formula, but in general it's not associative, unless your connection is flat. And here is an absolutely horrible formula for Q star. So I'll try to give you some hints of this. So I use beta. So I describe for you beta in a heuristic way. This is non-rigorous, but it gives you an idea. Beta, if you have a direction on some point x, TV, say, you can make it a vector field by extending it around x by parallel transporting along geodesics starting from x. Okay? So it gives you a vector field beta of TV. Okay? So S lambda of TV and W, what is it? It is exactly this vector here. It is the parallel transport of the direction SW, small w. Okay? And again, I do the beta trick to get a vector field. So now I follow two flows of the vector fields. So I must follow the flow of the vector fields, which is the Baker-Campbell-Hausdorff series applied to this. And then I have to use beta inverse, whatever it is. Okay. And then you get your double exponential direction. Okay. So it is proved in Gavrilov's papers that this guy is a tensorial quantity. It's by no means trivial, but it can be shown. And tensorial quantity, that means that okay. Now, yeah, the evaluation at x depends only on the two directions here, and it doesn't depend on the values these directions could take around x. Okay, so I'll end up my talk by describing a few results we get. First of all, now this beta I tried to describe in a quite fishy way. It is a true map described by Gavrilov. Beta goes from the vector fields to the vector fields, or I should say from the suitable completion to itself. Okay, and it makes all this diagram commute. So here you have the beta. Here you have natural injections of the vector fields into their free Lie algebras. Here you have post-Lie-Magnus expansions, one for G tilde and one for G, suitably completed, of course. Here you have Gavrilov's K-map, and here you recognize the diagram we already saw, the rightmost diagram we already saw. And here is the two different ways to express beta according to you do this or you do that. Okay. We obtained a quite intriguing identity. So this lambda this is basically the parallel transport of this direction. No, the parallel transport of the direction W along the geodesic of given by this. And okay, we have two expressions for this parallel transport. The left-hand side is a Postli expression, so because it uses the Postli-Magnus expansion. The right-hand side is a purely magmatic expression. It just uses the triangle. So what is this this guy here? So it is expanded like this up to order 3. And first of all, what is delta V? Delta V is the unique derivation of the free magmatic algebra generated by two generators V and W, such that delta V of V is equal to V triangle V, and delta V and W of W is equal to V triangle W. Okay, so let us look at this expansion here. So it starts with V, W, and then you have minus TV triangle W. And here it's more complicated because you have to use the derivation property. So if you apply delta V twice to W, you get a sum of 2 terms. You have alternate signs, and at order 3 you get a sum of 5 terms. Okay. So now we gave an explicit expression for all this in terms of planar binary trees. So you know that if you write a word with a non-associative operation, you have to decide how you parenthesize the word. And this is the same as putting the letters on the leaves of a binary tree, and according to the shape of the binary tree, you put the parentheses accordingly. So, for example, here you have the left comb, and here you have the right comb. And here, if you display the trees, the planar trees with 4 leaves, you have 5 words corresponding to the famous pentagon. And here you have the left comb, here you have the right comb, etc. And what is interesting is the factor 2 here. So why is it so? Because you have okay, you have 5 planar binary trees. So I think I display in the correct order. Okay. Now, okay, that's fine. So now look at these 5 trees. Now I want to put, it's a trick by Lode-Ronco. I want to put some levels on the trees. I have no choice for the 4 first ones, but here I can decide whether I do this or that, right? And that's why I have this factor 2 here. And binary trees with levels are essentially in bijection with permutations. And so you have this Lode-Ronco surjection from permutations to planar binary trees. And the coefficient here, okay, for this, sorry. Okay. Thanks. Okay. So the coefficient here, this L tau here, is for the number of permutations you have above a given tree, or if you prefer, the number of possible levelings of your tree. Okay. So just to finish this talk, we got a slightly simpler expression for the Gavrilov double exponential. This BCH dot is just the Baker-Campbell-Hausdorff series, but for the thin bracket. And you can see that the expression is maybe not very beautiful, but it's slightly simpler than the first one. And with this, we could reprove the tensorialness of this quantity. And with that, I thank you very much for your attention.